Hello everyone. Today we would like to study the chapter 2 of AI. So the title of this chapter is Understanding a Flower. One of the key applications of artificial intelligence AI is classification technology, which systematically processes various types of data such as images, sound, text, and videos, extract features from them, and categorize them. The core of classification task lies in identifying the distinct characteristics of data and determining the categories they belong to. This chapter uses flower classification as an example to help you understand the concept and applications of classification. 2.1 Classification Task. Classification is one of the fundamental techniques in AI used to solve the problem of extracting features from data and categorizing them. In AI systems, data serve as carriers of information. Different types of data, for example, images, sounds, or text, can be identified and processed using AI technologies. By using the example of a flower, we learn how to distinguish between different types of flowers from image data. 2.1.1 Diversity of data type. AI can process a variety of data types, including image data, for instance, features like shape, color, and textures of flowers in photographs. Sound data, for example, background sound describing the flower's environment. Text data, such as descriptions of the flower's name, species, or characteristics. Video data demonstrating the flower swaying in the wind or its growth process. The following table illustrates the applications scope of AI handling different types of data. Now is the data type and application example. For images, to identifying the type of flower. For sound, analyzing background sound to determine the environment. Text, searching for information about flowers. Video, tracking the growth process of a flower. 2.1.2 Case Study, Classifying Roses and Wild Roses. Roses and wild roses are two similar yet distinct flowers. Using AI technology, we can distinguish between them through features found in image data such as roses have more petals arranged densely, typically come in red, pink, or white. Wild roses have smaller and sparser petals with a more delicate overall appearance, a wider range of colors, and serrated edges in their leaves. The following table summarizes the distinguishing features of rose and wild rose. The feature is petal shape. For rose is dense and full. For wild rose is sparse and delicate. The color for rose is primarily red, pink, or white. For wild roses, there are diverse colors. The leaf edge for roses is smooth, and for wild roses is serrated. Through the above classification technologies, AI can systematically assist in understanding and distinguishing flower categories. This capability is not only applicable to flower recognition, but also widely used in areas such as medical diagnosis, logistics, coding, and image retrieval. 2.2 Identifying features. In these sections, we discuss how to extract features also known as features from data. Using flowers as an example, a flower's feature might include the length and width of its petal. We can represent the length is XXX and the width is YYY. Together, XXX and YYY form a structured set of data called a vector. Representing objectives as vectors. When an object can be represented by a vector, mathematical operations on vectors can be introduced. These operations include vector addition and subtraction, vector multiplication, and dot product. For example, if two flowers are represented by vectors A, x1, x2, and B, x2, y2, the vector addition A plus B is x1 plus x2 and y1 plus y2. The vector subtraction is A minus B is x1 minus x2, y1 minus y2. The dot product A dot B is x1, y2 plus y1, y2. These operations allow us to perform mathematical analysis of relationships and similarities between objects. Measuring similarity between vectors. The similarity between two vectors can be expressed by the distance between them. For instance, consider 2 points, point 1 at the position x1, y1, z1, point 2 at position x2, y2, z2. The distance d between these 2 points in a three-dimensional space is calculated using the Euclidean distance formula. D equals square x2 minus x1 square, y2 minus y1 square, plus z2 minus z1 square. The application to flowers. By representing the features of flowers as vectors, AI can systematically calculate the difference or similarities between flowers. For example, the length and width of petals can be measured and analyzed to classify flowers into different categories or identify specific species. This mathematical approach forms the basis for more advanced AI techniques such as clustering and classification. 2.3 Building a classifier. In this section, we will discuss how to construct a classifier using the classification of roses and camellias as an example. We will also explore the process of training and optimizing the classifier. So, what is a classifier? Suppose we have data or roses or camellias, including their length and width. These data points can be plotted on a coordinate plane. To distinguish roses from camellias, we can draw a line that separates them. This line is known as a classifier. So a classifier can be represented as a function f x1, x2, xn is a1 x1 plus a2 x2 plus an xn, where x1, x2, xn are feature vectors and a1, a2, an are weight parameters. Comparing human learning and AI training. The process of training a classifier is somewhat similar to human learning. Humans learn and take exams to solve problems. AI training, AI systems train and test to optimize the classifier for broader application. The following table illustrates the difference between human learning and AI training. Humans use continuous learning and take exams and solve problems. And AI use continuous training and conduct tests and apply it broadly. And then testing a classifier. After gathering a large dataset of rows and camellias, we can extract their features and associate them with their respective categories. These data points and features form the training set. Using the training set, we can experiment with different functions to construct a classifier and apply algorithms to optimize its performance, ensure successful classification. Perceptron. The perceptron is an algorithm used to train linear classifiers. Its principle is to adjust the parameters of classifier iteratively to correctly classify data points that were previously misclassified. Loss function. A loss function is introduced during the training process to measure the accuracy of the classifier. Suppose there are n training data points. The loss function represents the total classification errors. Mathematically, the loss function can be expressed as L equals summation maximum z minus yi gxi summation from 1 to n, where xi is feature vector of the ith data point, yi is label of the ith data point, plus 1 or minus 1. Gxi is the output of the classifier. Optimization is the process of adjusting classifier parameters to minimize the value of the loss function, thereby improving classification accuracy. The support vector machine (SVM). The support vector machine (SVM) is an effective classification technique. Its core concept is the classification margin, which measures the distance between data point and the separating line. A large distance indicates better classification performance, support vectors, and loss functions. In SVM, the data point closest to the separating line are called the support vectors. The loss function of SVM is defined based on the sum of the distance of these points. Like the equation L is 1 divided 2 W square C times summation of maxing 0 from 1 minus Y W Xi plus B, where W is the weight vectors of the classifier. Xi is the feature vector of Z data point. Yi is label of the ith data point. B is the bias term. C is the regularization parameters, balancing the weight between margin size and classification error. The advantage of SVM. SVM performs exceptionally well in situations where data can be linearly separated, offering high classification accuracy and excellent generalization capability. By using techniques like perceptrons and support vector machines, we can effectively train classifiers for accurate classification across a wide range of applications. 2.4 Testing and applications. After learning two classification algorithms, the perceptrons and support vector machine (SVM), we can use the trained classifier to evaluate their effectiveness. Testing is a crucial step to determine how well the classifier performs on new data and to assess its practical utility in real-world scenarios. While testing is important, once a classifier is built, it's essential to evaluate its performance. A good classifier not only performs well on the training data but also generalizes effectively to unseen data. This evaluation ensures that the classifier is robust and reliable for practical applications. Classification accuracy. To measure the performance of classifier, we use classification accuracy. This matrix is defined as a ratio of correctly classified samples to the total number of samples. The classification accuracy is equal to number of the correctly classified samples divided by total number of samples and times 100%. A high classification accuracy indicates that the classifier can effectively distinguish between different categories in the dataset. The testing process. 1. Split the dataset. Divide the dataset into two parts. The training set used to train the classifier. Test set used to evaluate the classifier's performance. Classification on test set. Apply the classifier to the test set to categorize each data point. Evaluate the result. Calculate classification accuracy and other metrics like precision, recall, and F1 score to analyze the classifier's strengths and weakness. The example scenario. Consider a dataset containing flower type, roses, and camellias, along with their feature vectors, for example, petal length and width. After training a classifier on the training set, we test it and the test set to see how accurately and it can distinguish between roses and camellias. Beyond accuracy, while classification accuracy is a simple and useful metric, it's important to consider other performance metrics. The precision measures the proportion of the correct predicted positive samples among all predicted positive. Recall is a sensitivity measures the proportion of actual position samples that were correctly classified. F1 score, the harmonic mean of precision and recall, providing balanced measure of performance. Applications of classifier. Once a classifier is tested and its performance metrics are satisfactory, it can be deployed for a real-world task. For instance, medical diagnosis, classifying disease based on patients' symptoms and test result. Image recognition, identify objects, animals, or people in images. Spam detection, classifying emails as spam or non-spam. Autonomous system, guiding robot or self-driving car by classifying objectives in their surroundings. Now, continuously improvement. Testing and applications are iterative process. If a classifier performance is suboptimal, adjustment can be made, including adding more data to the training set, optimizing the algorithm's parameters, exploring advanced algorithms to improve accuracy. By rigorously testing classifiers and applying them to practical problems, we can ensure their reliability and effectiveness, paving the way for successful deployment in various fields. 2.5 Multi-class classification. In previous sections, we discussed how to classify two categories of objectives, which is known as binary classification. However, in real-world scenarios, we often need to classify multiple categories of objectives, a process referred to as multi-class classification. Concept of the multi-class classification. The flower as an example, we aim to distinguish between rose, camellia, lotuses, peonies, and plum blossoms. To accomplish this, we need to design a specific classifier to each type of flowers. By inputting the feature vector of flower and comparing it with this classifier, we can determine which category it belongs to. Below is a sample example diagram illustrating the multi-class classification process. Insert diagram here. So the diagram include input factor vectors, a set of classifier, and corresponding output for multiple categories. The Softmax function for the normalization in multi-classes classification. Since the quantity of different categories may vary, it is essential to normalize the output value to range between 0 and 1. It is achieved using the Softmax function. The Softmax function converts the output of each classifier into probability value, ensuring the sum of probabilities across all categories equals to 1. The formula for Softmax is as follows. P of y equals I divided x equals exponential zi and summation I1 to n exponential zi. So where zi is the output value of the classifier for the ith category, n is the total number of categories. After Softmax computation, we can obtain the probability of the object belonging to each category. For example, a Softmax result might indicate a 6% probability of being a rose, 30% for camellia, and 10% for lotus. Multi-classification is widely used in real-world applications such as handwriting, digital recognition, image categorization, and medical diagnosis. 2.6 Application of binary classification in daily life. Although binary classification seems straightforward, it has a broad range of applications in various fields, especially in everyday technologies and systems. Below are some type examples. 1. Face detection in cameras. Face detection in camera is a classic application of binary classification. The problem is determining whether a specific area contains a human face. The solution is use binary classification technique to classify the area as a face or non-face. So implementation, train a classifier to analyze pixel features in an image and determine whether it represents a face. The second is cancer detection. Binary classification is critical in medical diagnostics, especially in early cancer detection. The problem, based on medical results, classify tissues as a benign or malignant. Solution, input patient data. For example, imaging or blood test result into a classifier to predict the presence of cancer. Benefit classifier assists the doctors in efficient and accurate diagnosis, particularly when handling large data sets. Spam email filtering problem. Classifying email as a normal or spam. Solution. Analyze email content, subject and line, and sender information using binary classification technique. Credit card fraud detection. The problem is determine whether a transaction is fraud. Solution is use transactions data, for example, amount, time, location, for classification to identify suspicious activities. And this example highlights the practical value of binary classification in various domains. 2.7 Summary of this chapter. This chapter introduced the fundamental concept and applications of classified in machine learning, focusing on binary and multi-class classification problem. The key takeaway: binary classification explored the design and applications of perceptrons and support vector machine (SVM) classifiers along with methods for testing classification accuracy. Multi-class classification discusses how to handle problems involving multiple categories, including input feature vectors, multi-classifier design, and the use of Softmax function. Practical application. Binary and multi-class classification techniques are widely used in face detection, medical diagnostics, spam filtering, and more, showcasing their significance in daily life. So, looking ahead, as data volume and application demands continue to grow, classification techniques are expected to become more efficient and intelligent. So this chapter lays a solid foundation for exploring more complex classification algorithms and discovering new possibilities in machine learning. So now I would use the Chinese for explanation. 接下来我们用中文跟各位解释第二章的内容。第二章的标题就是认识一朵花。人工智慧的应用之一就是分类技术，它能够系统化的处理各种类型的数据，包括图像、声音、文字以及影片等，从中提取特征，并且将它归类。分类的任务的核心在于找出数据的不同特点，然后进一步判断它所属的类别啊。那么在这一章里面，我们用花卉分类为例来帮助你理解分类的概念跟应用。2.1就是分类的任务啊。分类是人工智慧中的基础技术之一啊，用来解决从数据中提取特征并加以分类的问题啊。在人工智慧的系统中呢，数据是信息的载体，不同类型的数据，例如图像、声音或文字，可以通过人工智慧技术进行识别和处理。我们以一朵花作为例子，从图像数据中学习如何区分不同种类的花。2.2.1数据类型的多样性啊，人工智慧可以处理的数据类型包括图像数据，例如照片中花的形状、颜色和纹理特征；声音数据，例如描述花朵环境的背景声音；文字数据，例如描述花朵的名称、种类跟特性；那影片数据展示花朵随风摇曳的姿态或生长的过程啊。那么下面这个图表展示了人工智慧在处理不同的数据类型中的应用的范畴。那么呢，这个数据包括图像、声音、文字、影片等等。那应用的示例就是识别花的种类、分析背景音辨识环境、搜寻花卉的资料，还有追踪花的生长过程啊。2.1.2是案例分析，就是玫瑰跟蔷薇的分类。玫瑰和蔷薇是两种相似但不相同的花卉。我们采用人工智慧技术，可以通过图像数据中的特征来加以区分例如说，玫瑰呢，它的花瓣数量较多排列紧密，通常为红色、粉色或白色。蔷薇呢，花瓣较小，而且稀疏整体形态较为纤细，那颜色多样，而且叶片边缘具有锯齿状那我们以下的图表就总结了玫瑰跟蔷薇的特征的对比。那么这个特征包括花瓣的形态、颜色跟叶片的边缘。玫瑰是密集而丰满，那以红、粉、白为主，那是平滑的。蔷薇是稀疏而且纤细，那色彩多样而且是锯齿状的所以通过以上的分类技术，人工智慧可以协助我们系统化的理解和辨别花卉的类别。那这不仅应用在花卉的一个识别，还广泛应用在医疗诊断、物流分拣、图片检索等的领域那我们在这边可以大家也可以试着用2个插图来做数据类型跟应用范围的表。那么这个图我们可以其中展示出人工智慧如何处理影像、声音、文字和图片那么其次呢，我们 们可以做一个图，做玫瑰跟蔷薇特征的对比我们用这两个图像来表达两者的差异，例如说是花的形状跟叶片的细节等等2.2是找出特征我们在这些小节中将讨论如何从数据中提取特征，也就是 features 以花为例，花的特征可以包括花瓣的长度跟花瓣的宽度，我们可以用 xxx 表示长度，用 yyyy 表示宽度，那么这样 xxx 跟 yyyy 就构成一组结构化的数据，这个称为向量vector。那用向量表示物品当一个物品可以用向量来表示的时候，我们就可以引入数学上的向量运算。那这些运算包括向量的加法、减法、乘法以及内积等等。那应用在花卉上面的话，我们通过将花的特征表示为向量，那人工智慧可以有系统化的计算花卉之间的差异或相似性例如说，我们可以测量花瓣的长度跟宽度，进行分析来将花分类到不同的类别中，或者是辨识特性的品种。这种数学方法更为高级的人工智慧技术那么包括聚类跟分类来奠定了基础例如说，我们假设两朵花的特征，我们分别用 A 等于 x1 y1，B 等于 x2 y2 来表示。那么在向量的加法 A 加 B 就是 x1 加 x2 y1 加 y2， 向量的减法就是 x1 减 x2 y1 减 y2， 向量的内积就是 x1 y2 加 y1 y2。 那这些运算可以帮助我们进行物品之间关系的相似性的数学分析那么在接下来我们要测量向量之间的相似性两个向量之间的相似性可以用它们之间的距离来表示例如说，假若有两个点点1的位置是 x1 y1 z1， 点2的位置是 x2 y2 z2， 那么这两个点在三维空间 D 的距离可以用欧几里得的距离公式来计算，就是 D 等于开根号 x2 减 x1 平方加上 y2 减 y1 平方加上 z2 减 z1 的平方那所以我们在最后用一个图表来归纳我们在这一章里面所学到的一些内容那 2.3 是做一个分类器在这一小节我们讨论如何建构一个分类器。那我们用玫瑰花跟蔷薇的分类来来进一步探索分类器的训练跟优化的过程首先，什么是分类器假设我们有很多玫瑰花跟蔷薇的数据，这些数据展示了它们的长度跟宽度，我们可以在坐标平面上画出这些数据点，并且画出一条线将玫瑰花跟蔷薇分开来，这条线就是分离器。那分离器可以用一个函数来表示，就是 f(x1 x2 到 xn) 等于 a1 x1 加 a2 x2 再加一直加到 an xn。那其中呢 x1 x2 到 xn 是特征向量， a1 a2 到 an 是权重的参数。那么人类的学习跟人工智慧训练的比较就如下分类器的训练过程跟人类学习过程有相似的地方人类的学习，人类是通过学习与考试来解决问题，那人工智慧的训练是人工智慧系统通过训练跟测试来优化分类器，以便广泛应用在不同的场景那么以下的图表就展示了人类的学习跟人工智慧训练的差异人类是不断的学习，那使用考试要解决问题，那人工智慧系统是不断的训练，那使用测试来做广泛的应用那接下来是训练分类器。那么在获得大量玫瑰与蔷薇的数据后，我们就可以提取它们的特征，并且建立对应的类别那这些数据跟特征组合成为训练集，就是 training set。那利用训练集，我们可以尝试不同的函数来 建构分类器且利用演算法就是 algorithm 来进行优化，最终实现成功的一个分类那感知器就是 perceptron， 感知器是一个用在训练线性分类的演算法它的原理是通过调整分类器的参数或被错误分类的数据得到正确的分类那损失函数就是 loss function。我们在训练的过程，我们引入损失函数来衡量分类器的准确性，并且假设有 n 个训练数据，那损失函数是这个数据的分类错误总和。我们使用数学符号，那么损失函数就可以用 L 等 summation 1 to n maximum 0负 yi g xi 那么在其中呢 xi 是第i 个数据的特征向量 ，yi 是第i 个数据的标签在正一跟负一之间，那 gxi 是分类器的一个输出接下来是有关优化optimization。那优化是调整分类器参数的一个过程，它的目的就是使损失函数的值是达到最小，那从而提升分类器的准确性。支持向量机就是 Support Vector Machine (SVM)。支持向量机是一种有效的分类技术，它的核心概念是分类间隔，就是 Classification Margin， 也就是数据点到分类直线的距离。那距离越大分类效果越好。那再过来是支持向量与损失函数，在支持向量机里面跟分类直线最近的数据点称为支持向量，也就是 support vector。支持向量机的损失函数就是基于这些数据点的距离总和来定义所以这边有一个 L 等于1/2 W 的平方，再加上 C 乘上 summation i 等于1到 n maximum 的01到 yi wx xi 减加 b 那么在其中里面 W 是分类器的权重向量， xi 是第i 个数据点的特征向量， yi 是第i 个数据等的标签，那 b 是偏置项， c 是正常化参数用在平衡间隔跟分类器的错误的权重。那 SVM 的优势就是支持向量机在数据可线性分割的情况之下，能够达到非常高的分类准确性，而且具有良好的泛化能力2.4 是测试跟应用。那么学习了感知器和支持向量机 SVM 这两种分类器的学习算法之后，我们需要对训练出来的分类器进行测试，来评估它的性能和实际应用的效果。那测试是训练分类器是否能够成功应用在实际场景的重要的步骤。那为什么测试很重要呢？当分类器建完了之后，评估它的表现是很重要的一个好的分类器不仅能够在训练数据上取得好的结果，而且还需要对未知数据有良好的泛化能力。所以透过测试，我们可以确保分类器的稳定和可靠。那分类的准确率就是我们要衡量分类器性能的一个常用指标是分类的准确率。那么它的定义就是正确分类的样本数跟总样本数的比例，也就是分类准确率就是正确分类的样本数除以总样本数乘上100%。一个高分类准确率就表明分类器可以很有效的区分数据集中的不同类别那么测试的过程就是数据的测试，数据集划分，将数据集分成两部分，一部分是训练集，就用来训练分类器，一部分是测试集，用来评估分类器的性能那分类测试集就将分类器应用在测试集每个数据点来进行分类那结果的评估就是计算分类器的准确率，而且分析其他指标例如精准率精确率 precision 那召回率就是 recall 和 F1 分数，来全面了解分类器的优劣势那有一个案例场景，就是 用包含花卉类型，例如说玫瑰跟蔷薇，以及特征向量，例如花瓣长度跟宽度的数据集来例啊。那么把训练好的分类器应用在测试集，那检查它是不是能够准确的区分玫瑰跟蔷薇的一个超越准确率是，虽然分类准确率是一个很实用的指标呢，但是我们也需要考虑其他的性能指标，一个是精确率，就是 precision， 在所有被判定为正类的样本中呢，实际正类样本的比例，那召回率就是 recall， 在所有实际正类样本中呢，被正确判定为正类的比例。那 F1 分数是精确率跟召回率的调和平均数，用在综合评估分类性能啊。分类器的应用，当分类器的测试结果达到理想指标之后，就可以投入实际应用。例如说是医学的诊断根据患者的症状和检查的结果来进行疾病的分类影像识别就是识别图像中的物体、动物或者是人。垃圾邮件过滤就是把电子邮件分类为垃圾邮件或正常邮件。再过来是自动化系统，就帮助机器人或自驾车判断周围中的对象类别再过来是持续改进就是测试跟应用是反复迭代的过程。如果分类器的表现不佳，我们可以通过以下的方法来改进。一个是增加训练集的数据量，第二个是优化算法参数，第三个是探索更高级的算法来提升准确率。那通过严格测试分类器，并将其应用于实际问题，我们可以确保分类器的可靠性跟有效性，进而在各个领域成功部署和使用。2.5 是进行多类别的分类在前面的学习中，我们讨论了如何对两类物体进行了分类，这个被称为二分类binary classification。然而在实际的生活上，我们常常需要对各种类别的物体进行分类，这个被称为多分类，就是 multi-class classification。那多分类的概念呢，以花卉为例，我们希望玫瑰花、蔷薇、荷花、牡丹花和梅花等多种花卉进行区分。为了要完成这个任务，我们需要为每种花设置专门的分类器，并且将输入的花卉特征向量跟这些分类器进行比对，那从而确定花属于哪一个类别那么以下是一个简单的流程图的示例，那展示了多分类的过程。OK， 那么这个我们需要画一个图，然后包括输入的特征向量、分类器的组合以及对应的多类别输出归一化指数函数就是 Softmax。在多个分类中，由于每个类别的可能性需要进行比较，因此我们引入归一化指数函数，就是 Softmax。Softmax 函数将每个分类器的输出转换成为一个概率值，来确保所有类别的概率总和为1。所以 Softmax 它的数学公式就是 P y 等于 I over x 那等于呢 exponential zi 加上 summation j 1到 n 的 exponential xi 那其中呢xi 是分类器对第i 个类别的输出值n 是类别的总数那经过 Softmax 计算后，我们知道输入物体属于哪一个识别的概率。例如说，某个物体的 Softmax 可能显示它是玫瑰花的概率是 0.6， 它是蔷薇的概率是 0.3， 而是荷花的概率是 0.1那多分类的方法广泛应用在实际的场景面例如说手写数字的识别、图片的分类医学的诊断等等。2.6 是二分类在日常生活中的应用。二分类法虽然看来简单，但是它的应用场景非常的广泛，尤其是在许多日常生活中的技术和设备中。那么以下是一些典型的应用：一、相机中的人脸检测。相机中常见的人脸检测功能就是二分类的典型应用之一那问题的描述就是要判断一个区域是不是人脸。那解决的方案就是利用二分类技术，将区域划分为 人脸或非人脸。那实现的方法就是训练一个训练器，输入影像中的像素特征啊，然后判断是否属于人脸。那么癌症检测二分类法也在医学检测中有重要的应用，尤其是在癌症的早期诊断率啊。那问题的描述就是根据检测的结果判断病变组织是良性还是恶性。解决的方案就是将患者的数据，例如影像、血液检测结果等等，输入分类器，那预测是不是有癌症。那优势就是分类器可以辅助医生进行高效而且精准的诊断，尤其是在大量样本的情况下。那垃圾邮件的过滤问题的描述就是我们判断一封电子邮件是正常邮件还是垃圾邮件。解决的方案就是利用二分类技术，将邮件的内容、主题、发件人等特征进行分析。再过来是信用卡诈欺的检测问题的描述就是说，我们要分析这个交易是不是存在着欺诈的行为解决的方案就是利用交易数据，例如金额、时间、地等那进行分类，那判断交易是不是正常。那么这些应用呢就展示了二分类技术在多领域中的实际上的一个价值那本章的内容我们在这边做一个小结在这一小节里面，我们介绍了机器学习中的分类器的基本概念以及它的应用，并且分别讨论了二分类和多分类问题的解决方法跟实际的场景。本小节研究这一章主要的内容包括二分类，就学习了感知器和支持向量机两种分类器的设计跟应用，并且了解了如何测试其分类的准确率二是多分类介绍了处理多分类问题的方法包括特征向量输入、多分类器设计以及 Softmax 函数的使用第三个是应用场景，也就是说二分类和多分类技术广泛应用在人脸的检测、疾病的诊断、垃圾的邮件过滤等等领域，那展现了它在日常生活中的价值未来的展望就是随着数据量和应用需求的不断增长，分类的技术将会变得更高效能跟智能。所以我们这一章呢，就为我们后续的更复杂的一个分类演算打下一个很好的一个基础，帮我们来做未来探索的一个可能性的提升所以我们今天的课程就讲到这边谢谢各位的收听学习我们下一次课程再会。